Welcome back. We are going to go to block 3 now, the third more or less hour of our seminar today. We're going to talk about formulations that are actually providing AC feasible solutions. And we're going to focus a little bit more on these two blocks now, more on the power flow formulations and also some new kind of technique on trying to solve non-convex problems. So the first one that I'm going to discuss is the semi-definite relaxation, the SDP relaxation. You learned a lot of things on Monday, Tuesday from Stephen on what really the SDP means. Here I will show you an example of how you can transform an SDP problem from a deterministic to a scenario-based problem. So here the case study I will show you later on, okay, includes also N-1 security constraint. It includes uncertainty in the way I have been talking about, but also I do some extra control policy for the AVR of the generators. So I will allow here some connection between the uncertainty and the AVR and the AVR control. This is, for example, the AVR based on the forecast, and this will be the AVR set points after the having the scenario of the uncertainty. I'll go a little bit quickly on summarizing the changes. You remember we're talking about the relaxation that depends on a set of constraints that are semi-definite. So you can write the constraints of the ACOPF with the transformation of the decision variables to a decision variable W that contains the real and imaginary parts of the bus voltages. And you can easily write the constraints in this way afterwards. But in the end, there is the issue that there is one rank 1 constraint over here that we don't like so much. It creates the non-convexity in the problem. But if we take this out and also put that the W for a specific bus is 0, that corresponds to the reference of a specific bus, then we are able to have a relaxed problem, and it's convex at this point. We have this extra specification of the reference angle that we are putting over here, and now we are looking of how we are changing the rest of the constraints of the problem in order to accommodate the deviations that may happen due to the forecast errors. So we said before about the AVR corrective control action that we allow, but we are also going to assume the same kind of steady state point as we mentioned before about the AGC. So we are going to have a mismatch because of the forecast error or because of the outages. It's going to be distributed to the generators, and then you will have a new dispatch. Similarly, this will happen for the voltage of the generator. And this is something, basically, this kind of constraint can be represented by this, connecting, for example, the different kind of W's for each scenario that we take into account. Because remember that the W is the voltages that for the different scenarios we are taking into account, they're going to be changed. The profile over all this voltages will be changing. So here you see, for example, we have outages. because of some of specific outages, we have that, let's say, generation outage we need to compensate by adjusting the generators. And this is shown here, that the pre-disturbance operating point of the system with this W0 is going to be now transformed to a new operating point WI, and it has to have this link of this function that really shows us that this change in generating power will be satisfied. So we do have the extra assumption here that it's not an assumption regarding the uncertainty that starts because also this kind of WI, so the I is with respect to the outage, W for a specific outage or specific case, for example, depends on what is the forecast error. So with different kind of input from the renewable source that we have, we're going to end up with a different voltage profile. So this is here to highlight the fact that yes, this kind of voltage depend on the scenarios that we are going to use, but in order to facilitate the tractability, we will do the assumption here that the voltages, as I mentioned, this is for the AVR only. So the voltage of the generators are going to follow this kind of rule that will depend on the forecast error. And this helps a little bit the calculations. So this is some results for a 14-bus system, where I guess a similar type of results. Here is on this axis, you see the probability of insecure carriers, the empirical probability, when we have tested for 10,000 wind realization that we have not, of course, used in the optimization. And I show you two different formulations. The one is here, the AC based on the STP relaxation, that you see it has very low probability of having insecure cases. The violation level epsilon, we had it again at 10%, and again you see that it satisfies very well this theoretical violation. The other case study we saw here is the DC, based on the DC assumption, the DC power flow assumptions, and this means that we have a linearized system, and with extra that we are assume all this assumption with the DC case with the voltage to be equal to 1 as well. So this is the case that actually shows that for a specific setup that we have here, this kind of parameters, it's very easy to see that the approximation is not working very well, and the empirical probability of insecure cases at some point reaches actually the 100%. So these kind of points here really highlight that the system, the linearization that one can do at these points of the day is already outside the realistic limits based on the AC power flow. So yeah, that is to show that, okay, it's nice to do approximations, but in the case we need really to operate the system, we have to go through a little bit of more deeper thought on what kind of algorithms will be appropriate. So for this easily scalable cases I showed before, it might be that we do have this problem in reality. This is nicely solved here for using the SDP relaxation and this chance constraint, but it doesn't scale very well. So it's something that I will discuss another way that has some more promising scalability properties. So here, for example, for the 14 buses, and I did have, I don't remember, a few scenarios, ended up having really much time to run the optimization. Of course, it was also n-1, and I was having also a lot of scenarios, but it's not that good if we think that we have to go and scale to thousands of buses. And just realized I didn't have my video, sorry about that. So just to go and dig into these results on a specific line loadings. So you see that you have these 20 lines of this specific IEEE system I've used, and there are certain lines that are, as you see, outside the limits, the capacity limit of the line from the beginning. From the beginning, I mean from the forecast value and for all the scenarios that you take into account. So this is the model mismatch in the end that is created due to the approximation. One aspect that I want to highlight here is that the fact that we were able to use this kind of policy for the AVR, it also increased the controllability of our system. So the degrees of freedom we had of control were more, and hence we were able to obtain some lower cost of our objective function. So this is just a graph showing for certain hours of the day how the policy-based AVR set point performed a lot better with respect to costs, with respect to the case that the AVR, so the voltages on the generators, were kept constant. I didn't show all the hours here because for this constant AVR set point, they were not feasible for the rest of them. The problem was not feasible. So, what for the green one, the policy-based was actually. So I'll go back now to the randomized optimization that I have been talking. The results I showed before for the SDP, I used the convex scenario optimization because of the convex problem. But here I'm going to talk about another randomized optimization technique that is proved to work for non-convex scenario optimization problems. Still has the same kind of properties. Generally, it also uses samples to learn how to get the desired performance. It can generalize from seeing samples to unforeseen realizations. We do have confidence predictions. This time, though, they are done a posteriori, and I will explain in a bit what I mean. Basically, they cannot be made a priori as before, because remember before we were saying, okay, we want this epsilon, then we just select a number of scenarios from our pool, and then we are, let's say, with high confidence going to satisfy the chance constraint with this 1 minus epsilon probability. Here we cannot do that. The proofs are not yet that strong to go to that direction, but they work for as an a posteriori result. So you run your optimization, you see what has happened, and you can create the generalization characterization of the solution. So this is good as well. Not that good as before. No assumptions on the underlying distribution of uncertainty. This is something that this technique carries as well. And the very good extra that we get out of this optimization technique is that we can apply to non-convex problems. So the way it works basically is that we are assuming that we do have this non-convex optimization problem. Non-convex optimization problem that we want to minimize this objective function with subject to decision variables x that belong to a specific space that depends on the uncertainty. The uncertainty delta is now depicted as scenarios from the beginning, and we do have, for example, n scenarios to take into account in this setup. So one important thing to define here is the probability of the one existing specific solution of x, for example, not to belong in the set of x delta. So it means really that, okay, you have here the delta living in this space that your scenarios are taking from, and then it shows really the probability of the x not belonging to this kind of x delta. So in the end, what they want to end up saying is that they want to get a solution xn star that is feasible, that is satisfying this probability of violation in this way. So it is not really going to have a violation bigger than epsilon, because the probability of having a violation bigger than epsilon is going to be smaller than beta, and the beta is very small. So they want to have the xn to be feasible, meaning that the opposite of that is going to be satisfying this with 1 minus epsilon probability. So they end up with showing a proof that if you can end up with this result and achieve this kind of, let's say, guarantee, if you have an algorithm over here that the algorithm really is something that it really needs to describe your initial problem as well, right? So, but it can be manipulated that you can extract the solution of your initial problem, but do some other things as well. So if you really define your algorithm so as to get n number of scenarios, you run the algorithm and you get the solution x n star, and then you are able to use k, a very small number of scenarios, and also end up with the same exact solution, then you're able to use this formula they have built and satisfy the trans-constraint I saw just before, given though this epsilon. So this is epsilon that is something that is calculated a posteriori. In other words, if we see this example they have in their paper, if the scenarios that you want to fit your algorithm are, for example, 200. So if this is 200, and then you end up finding out the 50 scenarios that you can fit and get the same answer, then you put this number k and then inside this formula, and you end up having something up to here. So your a posteriori theoretical violation guarantees are very high in this case. If you end up, for example, reducing even the number of scenarios that you can take into account, for example, 2, 5, and you say, okay, with only 5, I can again achieve the same solution. Then you can see over here that the probabilities, for example, for the specific setup here, the probability of violation is a lot lower. So they prove that the fact that such an algorithm exists that provides this same output, and not necessarily an optimal output, it just has to be a feasible output that comes from the same algorithm, and it doesn't has to rely on the sequence of the data you're going to put into there. So this is one of the assumptions of the requirements as well, that you don't have to put any order. But anyway, these are minor requirements. The important thing is that if you manage to have such an algorithm, then you are very happy to enjoy this kind of a posteriori theoretical guarantees, even for a non-convex problem. All right, so what we will do now, we are going to see how we can create such an algorithm in here that is going to highlight a solution that is feasible for the AC optimal power flow problem. And before going there, I have to add one more line here in the table I had before to say that yes, with this approach, you can deal with any of the problems I'm talking about over here because it covers everything. The drawback is the a posteriori guarantees, as I mentioned before, and also the level of the guarantees as well, because maybe you get a posteriori guarantees, but they are also they can get very poor depending on the scenario you can get. Imagine, for example, if you have a problem, you are not able even from 200 to go to 150. You end up having some guarantees that are up here, and it's like there's no information over there because they tell you that okay, you might be violated even 90%. So you don't get any good information out of that. So the algorithm that we have built here in order to use this scenario-based optimization is shown here. So it is based on a ACQP OPF algorithm that is actually, as I mentioned, an iterative algorithm between a QP problem and an AC power flow check, where you update and you solve the QP optimization. You get a solution, you solve the AC power flow equations, and you go in this kind of round until you converge. So we have updated the classical ACQP that actually is based on just one value, one deterministic case, with connecting it with different scenarios that can appear, and then start to see how we can build this kind of case that we end up having the same solution of xn that requires here. So what we did is that we assume that we have this n number of scenarios that are coming. So this is the input n over here, and we start the algorithm. We do rank then wind scenarios according to some norm. This is just the first norm here. One could use whatever likes, and we do, after the ranking, we take the first one, we add it inside this SCQP with the additional set of constraints corresponding to the scenario. We do get the outcome, the solution, that actually shows the satisfaction of these specific scenarios that are included here. And we test what happens with the rest of the scenarios. That is an information that we have already entered in the whole algorithm over here. If there are violations due to scenarios, we end up adding again scenarios in the CQP based on observing different violations levels of the constraints. And as you do this kind of loops, you have one loop here and you have the other loop over here, you end up at some point that you don't violate at all any kind of the rest of the scenarios that you have been including inside the CQP. The thing is that the way that we have constructed this algorithm over here, whether you put n scenarios and you have an outcome that is like that, actually internally you have also identified the case scenarios that are solving the problem in the way we are building the algorithm. So as you solve that one time, you also know what are the case scenarios that you had entered in this optimization problem in this iterative ACQP algorithm. And having these case scenarios, it's also obvious that if you add the case scenarios over here, only the case scenarios, you will end up with the same solution xn star as well. So we end up having that for two different set of scenarios, we end up with the same solution. Of course, this k is a subset of an average scenario that is a subset of the set that corresponds to the n. And the trick would be if we could identify the smallest number of scenarios, k, that could result in this solution. So in the general case, the way that the people proved it in the non-convex optimization paper, scenario optimization paper, they were just saying that in order to reduce the number of k, you can use whatever method you like. So for example, you could start, if you have a problem with scenarios that you have included, let's say n number of scenarios, you have included and you get this xn star, you may start just arbitrarily deleting scenarios, and if the solution remains the same, you go and delete one more. If it is the same, you go and delete one more. This is one way, greedy way to do so when you have such problems that you have an n and you are looking like that to reduce to k. We did it on the other way around. We started with adding scenarios and checking when they are satisfied, but still in both directions there is some need for effort to find what is the minimum number of k to be leading to this same solution. So the ACQP, yes, I mentioned that it is the iteration between the AC power flow using QP solution. It can have a startup with different kind of initial power flow solutions, and these are the constraints for the QP part with regards to the additional scenarios that we take into account. We have a linearized problem, and then for each scenario we have different variables. And I'll show you the case studies here that are related to this problem. So we have this ACQP algorithm tested for the different networks. So we go from the 14th until to the 118 bus. The number of scenarios that we tested were up to 1,500 scenarios. We had this amount of uncertainty variables, and we assumed that the confidence level was very small. So basically, we had a very high confidence that we would like to have very high confidence that our solution will be robust with these epsilon guarantees. And we try to see what happens. Before we go to see what is going on with the this experiment to find the K number of scenarios, let's see how this ACQP performed, this just constrained ACQP performed with respect to the cost of operation, because in general, this ACQP is a heuristic method that there is no proof that it can converge to an optimal. So we were wondering, okay, how much far away we are. And we know that we can have the relaxation with the ASOCP that can bring us a lower bound of the cost. And we just checked how far away we are from that. So that means that if we are very close to that, we cannot be that far away from the true optimum. And this is the plot showing the difference here with the ASOCP, and shows that this was quite small with respect to cost, whereas the exact ACQP cost was plotted here. As just to direct you a little bit, so this is based on initiating the problem with different numbers of scenarios up to 1,500, different case studies. And for each of those, we run 500 independent scenario sets. So that's how the box plots have appeared over here, because we had a pool of scenarios, and then independently we were picking scenarios in order to end up having this kind of for every case here you see in the box plots for a 10 total number of scenarios, for example. Okay, so something to observe here as well is that the resulting cost, yes, is not far away from the lower bound that is provided by the ASOCP. And of course, the cost, as you see in general, is increasing since we end up satisfying the constraints for more scenarios. So this is something that, okay, it is quite expected. All right, so what we see, we are still here at the first case study of the EEE40 bus system. Still, we have all the cases of the different set of scenarios we have used and the box plot. And you see on the first plot, the percentage of violations, the percentage of scenarios that have AC power flow violations in an empirical way. So we do have, it's like, yes, a Monte Carlo analysis with 10,000 scenarios that we check the solution we got from this XN star solution we got from each of these problems. And actually from each of these scenario sets as well. So you have to run the optimization, get the solution, and then this solution is tested for 10,000 scenarios. And that's how this probability of violation is plotted. you see, for the cases that we are using a lot of scenarios, like 1500, the probability of empirical probability of violation gets very low, maybe below 1 here. I don't see very well. And while as we have smaller scenarios into our consideration, the probability is getting increased. The question now is how this is with respect to the theoretical guarantees that we can get out of this problem. So for each of the solutions that we have, for each case study and for each solution, for each scenario set as well, we do have the solution of X and star that is calculated, and it comes along also with the case scenarios. These scenarios that if we add into our algorithm, we're going to get the same output. And we are plotting here this number of scenarios. This is the scenarios K for all these case studies. And you see that it doesn't go beyond 4 in the beginning at all. And in general, it stays between 2 and 3 in many of in all these case studies. So you may imagine, because the K stays a little bit the same for all these case studies, that as more scenarios we are throwing inside the optimization problem that actually are satisfied, and we are putting that in this equation, we are going to get better guarantees, theoretical guarantees. We are plotting them somehow in this plot. Specifically, you see here in this plot the difference of the theoretical guarantees with the empirical probability of violation. So for each calculation, you get your theoretical, and then you compare with the empirical, and we have these plots over here. So for the cases of 10 or 50 scenarios that we take into account, you see that the probability, the difference in the probability of violation could be very big. So even if the theoretical was giving a very good kind of value, you will see that in the end, practically, you have a very big difference. So the thing is that at the moment, as you see that you go closer to 0 here, that is really showing how the theoretical also is very close to the empirical, and it's closer to what we would like to see as well. So some other examples with bigger networks are here. The 14 is the one that we tested for, and focusing now for the 1500 scenario cases. And again, we do have these box plots with 500 scenarios randomly picked from the pool. And you see that the theoretical probability of violation now that you can construct here after the solution is quite low, but still can be, in some specific cases, quite up to 4.5 for the 118. The problem with that is that we take what we have, we cannot control that. The only thing we can do in order to make this theoretical probability better is to devise kind of algorithm to reach a more optimal number for the case scenarios. So to minimize them, to minimize the number of those. So here you see that again, even though you have this kind of violation levels, the theoretical violation levels here, for different setups. The empirical probability is something that is very small. It is down here in the 0.5, and you may see now in this plot on the next. If you zoom in, you will see how it looks. For all these cases, the number of support constraints are shown now in this first plot. The number of the support scenarios are up to 9 in some cases in the 118 bus, but in general stays around the 5 scenarios. So it really depends on the way we have been selecting and the scenarios to enter, also the optimization. So we might just have selected a path that we are creating in some cases bigger or smaller numbers of scenarios. And on the right here, we saw also the execution time. It goes for, in some specific cases, up to a minute for this 118 bus. The thing is that the low number of the support scenarios is something that will be directly related to the computational time, because as many scenarios we have to incorporate in the optimization, then we need more time to deal with them. So we see we have these faster results for the low number of scenario support scenarios. So as we go here, and the good thing though is that even if we have some small number of scenarios in all these cases, the solution comes with these theoretical probabilistic guarantees that still had some good values. They were not useless. Maybe we were lucky, I don't know. This was the results based on not a lot of tuning of the problem. All right, so the resulting trans-constraint ACQP algorithm, it's something that I would like to conclude with some advantages. So the good thing about it is that we don't have model approximations, and then the solution that we get will be always feasible for the AC power flow constraints, and it does provide probabilistically robust solution, but with an a posteriori guarantee. So we need to go and do some trial and error with respect to how we are creating a K. But if we do find it, then yes, we do have the probabilistically robust solution that we want to. And the number of support scenarios may remain small as the problem size increases. And this is something that really highlights the promising scalability properties of this specific algorithm, because in the way we use it, we might identify quickly the scenarios that are going to be satisfying the big set of scenarios N, and that means that we are going to get to these generalization properties in a more accurate way. So that's it for this section. I guess I can take a couple of questions and go to maybe a 5-minute break or something, and then we will go with the rest, the 4 block and the optimization of reserves and energy.